सर
हा.
काय ते कॅमेरा मस्त
कॅमेरा चांगला नाही का?
वा एक नंबर कॅमेरा कान किती क्लिअर आहे.
हा माईक केलाच आहे. तुम्ही एकदा फक्त आवाज त्याच्यात थोडं एक दोन लाईन बोला. सर ब्लूटूथ कनेक्ट आहे का?
ब्लूटूथ कनेक्टेड असून
असेल ना.
करून
इथंच आहे ना?
इथं माहित पडेल कुठे इथं
हे इथं त्याच्या बाजूने ते ब्लूटूथ.
हा खाडे सर,
येस सर.
आता नाही का मी कॉल
नाही.
रिसिव्ह करणार नाही, कारण इंटरनेट मी मोबाईल वरून कनेक्ट केलं इकडे.
बरं बरं ठीक आहे.
कारण मोबाईल उचलला तर इथं डिस्कनेक्ट.
डिस्कनेक्ट.
नाही नाही आता मी कॉल नाही करत.
हा 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 म्हणजे मी आता कुणाचाच कॉल उचलणार नाही.
हा चालेल.
व्हॉट्सअप मेसेज करते.
हो व्हॉट्सअप मेसेज करता येईल. मी व्हॉट्सअप ऑन ठेवतो माझं काही असेल समजा तर, किंवा मग इथं मेसेज करता येईल तुम्हाला.
हे डॉक्टर किशोर सर.
नमस्ते सर.
मी सुद्धा डॉक्टर किशोर.
आणि सर
हो का? बरोबर
सर ह्या पल्लवी मॅडम पाटील मॅडम.
पल्लवी मॅडम.
नमस्कार. नमस्कार मॅडम. नमस्ते 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 नमस्ते.
करू सर ना वेटिंग रूम काढून टाकतो.
मी माझा व्हिडिओ बंद करतो थोड्या वेळासाठी, चालेल ना?
चालेल चालेल चालेल.
ओके ओके ठीक आहे.
हा आपल्याला मग त्यांच्या जागी त्यांचे हे स्क्रीन सोबत सायमल्टेनियसली तुम्ही लावतायत.
हा फक्त बाकीच्यांचे जे स्क्रीन आहेत ना ते अॅनोटेशन स्टॉप करा, कारण मुलं काही पण लाईन ओढतात मध्ये स्क्रीन.
नाही 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 सर अॅनोटेशन आहेच नाही.
नाही ना?
सर आणखी एक
बोला
सर
ना.
तुमची पीपीटी एक स्क्रीन पहिलं लावलं तरी मग चालेल. मग
हा 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 2 मिनिटं मी स्क्रीन लावून ठेवून देतो. 2च मिनिटं.
एकदम बॅक गेलं चालते काय? हो
हे अलाव केलं ना सगळं. कोणी स्क्रीनशॉट अलाव पाठवलं.
आणखी वेटिंग वर पाहू.
आता नाही सगळे इंटरव्ह्यू
आम्हाला काही
मी आहो ना.
तुम्ही काही जाऊ नका 2 घंटे. आणि प्रिन्सिपल मॅडमने काय हे घेऊन द्यावं लागेल का? हाच मोबाईल घेऊन जावं लागेल आहे ना जो चालू आहे तो समजा.
हो
त्यांना सांगून द्यावं लागेल ना.
मेसेज टाका. मॅडम ते पास करा तुम्हाला लाईव्ह.
बघा माझी स्क्रीन दिसते का? स्क्रीन दिसते माझी? स्क्रीन दिसते?
क्लास घेता.
फक्त एंड नाही दाबायचे.
आणि याला सोबत सांगितलं हे जर लाईन गेली तर हे बंद होईल. मग एक व्हॉट्सअप चालू करून ठेवू का? हा सर.
स्क्रीन दिसते का माझी?
उधर झालं.
स्क्रीन शेअर होतोय का? स्क्रीन शेअर होतोय बघा.
हे युट्यूब
खाडे सर स्क्रीन शेअर होतोय का?
तुम्ही आधी त्याला थोडं हे करा सर.
बंद केलं.
जो फोटो आहे ना तो हे करा सर. काय फोटो काढायला
डॉक्टर किशोर सर ऐकताय का मला?
फोटो काढा म्हणजे त्या व्हिडिओचा एक फोटो तयार करा तो हात जोडताना.
हो होते नंतर आपल्याला स्क्रीनशॉट.
कोण कोण जॉईंट आहे तर?
हॅलो ऐकू येत आहे माझा आवाज? खाडे सर.
हा सर.
हा सर.
स्क्रीन शेअर केली मी, दिसते का स्क्रीन?
हो दिसते.
यस यस सर.
मी स्क्रीन मोठी करतो.
चालेल
सर.
2 मिनिटं. दिसते का? हा आता पूर्ण स्क्रीन दिसते का बघा?
यस सर.
यस सर.
ओके बघून घ्या सर. आता ओके ना? फाईन
फाईन सर. ओके सर.
डॉक्टर किशोर सर फ्रॉम फिजिक्स डिपार्टमेंट सर.
ओके सर. थँक्यू
वेलकम सर. नाईस टू सी यू सर.
Thank you very much, sir. Nice to see you also, sir.
आता ते हे मॅडम तुम्ही तुमच्या ह्याच्यावर चालू नाही की मला आधी चालू करून घ्यावं लागेल. काहीच नाही, ते डायरेक्ट झालं अटॅच. हो त्याला बघ
हे बटन सुरू करा.
ते बटन चालू केले ब्ल्यू झालं लाईट तर आहे.
पण महत्वाची सेकंड मीटिंग जॉईन करून
चांगला आहे चांगला.
मग एक नंबर आहे, डिफरंट वाटत आहे.
चांगला नाही वाटलं आहे ना.
एक नंबर वाट राहिलं.
पार्टिसिपेंट्स हॅलो,
एक नंबर आहे.
कोणी गाणे वाजू नये.
पूजानुसार 14.
कोणी जर मदत वाजवलं की ह्या पहा.
आपला जे हे पण इथे फोटो तोही हे करणार आहे. तर तुम्ही काही जाऊ नका असं त्याचं.
ना मी आहो जातोच ना बसतो आपली
आणि आवाज बोला.
हॅलो
हॅलो
हॅलो हॅलो A very good afternoon to all. याच्यामधनं व्हॉल्यूम रेज होत असेल ना.
करा बरं तुम्ही बोला बोला आणि आवाज करा.
सुरुवात लेट इथं बोलायचं. हा ते दोन माईक असतात कॅमेरा दोन माईक इथे बोलायचं तुम्ही इकडे घ्यायचं बस जवळ जवळ
A very good afternoon to all. नाही येत आहे का? हा अटॅच करून बघू का सर?
तसा नाही तसा नाही थांबा एक मिनिट थांबा
आता ट्रॅव्हल सर बोला बरं.
हॅलो हॅलो आवाज येतो आहे
हो हो आवाज येतोय सर तुमचा आवाज येतोय.
मॅडम डायरेक्ट
हे बंदच करून डायरेक्ट बोलू का?
आवाज येतोय तुमचा काही प्रॉब्लेम नाही.
थँक्यू सर
ओके
डायरेक्ट किती झालं उद्या ना उद्या थांबा क्वेश्चन असं कसं क्वेश्चन येणार का
चालू आहे
मॅडम स्क्रीन दिसतंय ना? स्क्रीन दिसतंय ना? खाडे सर,
हा सर,
स्क्रीन दिसतंय का? स्क्रीन शेअरचा ऑप्शन गेला इथून.
बरोबर.
शेअरचा
ओके
option.
ओके ओके. करा सर आता.
करा सर. त्याची काही गरज नाही. आवाज
नाही, आवाज डायरेक्ट जातो.
येतो ना?
चेक केलं नाही सर. अरे वाजला सर.
सर
नाही, हा हा हा, आला स्क्रीन शेअरचा ऑप्शन आला.
आला ना?
हो, आलं.
हा,
राईट.
आली सर.
आले ना? हम्म.
नाही ना सर, ऑफ आहे ना. ऑफ आहे. कनेक्ट नाही होत आहे का?
नाही नेटचं माझं
त्या सरांचं जॉईन केलेलं होतं.
काय माझं मी दिलं तरी पार्टिसिपंट करून
तुमचं मग याला कोणाचं करू? माझ्या बंद झालं का?
नाही
पण ते इंटरनेट
सर मला एकदा
आलं
नाही. अच्छा नंतर हो. नाही ओपन करायचं तुम्ही इथे बसा.
सुरू करूया सर. बहुतेक 100 पार्टिसिपेंट झाले तिकडे.
आलेच.
यस सर.
सर किशोर सर,
हा बोला ना सर.
चालू कराई.
हो सुरू करूया. बिंदास.
ओके सर.
काहीच problem. ओके सांगा, करा सुरुवात तुम्ही.
Very good afternoon to all and my hearty welcome to all. Honorable President Shri Rao Sahib Shekhawat Sir, Honorable Mrs. Manjari Shekhawat Ma'am, President of GEMS Vidya Bharati Mahavidyalaya, Amravati, Honorable Secretary Dr. A.D. Chauhan Sir, Honorable Principal Dr. P.S. Yankar Ma'am, Honorable Dr. R.M. Patil Sir, IQAC and NAC Coordinator, Professor M.M. Rathore Ma'am, Coordinator of Research Cell, and all heads of the department, professors and researchers. On behalf of Department of Mathematics, Vidya Bharati Mahavidyalaya, Amravati, I, Pallavi Patil, welcome you all in this state-level webinar on Fundamentals of Fractional Calculus. It gives us an immense pleasure to have respected Dr. Kishore Kuchi Sir and respected Dr. P.P. Khade Sir, Head Department of Mathematics, and other organizing committee members. I once again welcome you all. We are privileged to have respected Dr. Kishore Kuchi Sir here to enlighten us. We are very grateful to you, sir, for having kindly accepted our invitation and for sparing your valuable time. Now I request Dr. Khade Sir to give introductory speech.
Very good afternoon, one and all present here, and thank you for joining. I extend my hearty welcome to Honorable Rao Sahib Shekhawat Sir, President Vidya Bharati Shaikshanik Mandal Amravati, Honorable Manjari Shekhawat Madam, Chairperson Vidya Bharati GEMS, Honorable Dr. A.D. Chauhan Sir, Secretary Vidya Bharati Shaikshanik Mandal Amravati, Honorable Dr. P.S. Yankar Madam, Principal Vidya Bharati Mahavidyalaya Amravati, eminent speakers Dr. Kishore Kuchi, Assistant Professor, Department of Mathematics, Shivaji University, Kolhapur, Dr. R.M. Patil Sir, IQAC and NAC Coordinator, Professor M.M. Rathore Madam, Research Cell Coordinator, Dr. S.P. Kandalkar Sir, Professor and Head, Department of Mathematics, GVISH Amravati, Dr. S.D. Katore Sir, Head, Department of Mathematics, Sant Gadge Baba Amravati University, Amravati, Dr. D.D. Pawar Sir, Director, School of Mathematical Sciences, Swami Ramanand Tirtha Marathwada University, Nanded, Dr. V.R. Patil Sir, Arts, Commerce and Science College, Chikaldara, Dr. V.G. Mete Sir, Professor, RDIK and KD College, Badnera, and all learned dignitaries, distinguished invitees, teachers, and students. I welcome you for this online webinar on Fundamentals of Fractional Calculus. It is indeed a matter of immense pride for me to be here today to welcome you all to a very special and momentous occasion of Department of Mathematics, Vidya Bharati Mahavidyalaya, Amravati. Department of Mathematics started in 1972. Department has recently started postgraduate program in mathematics. It is noteworthy to mention our 4 students selected and successfully completed Mathematics Teach and Talent Search program organized by IIT Bhilai and VNIT Nagpur in 2019-20. The department organizes many student-centric activities regularly. Today, we have the unique honor and privilege of listening to the Dr. Eminent Scientist of Mathematics, Dr. Kishore Kuchi, who will speak on fundamentals of fractional calculus. Dr. Kishore Kuchi, presently working as Assistant Professor, Department of Mathematics, Shivaji University, Kolhapur. His area of research is fractional differential equations, abstract differential equations, integral inequalities. He has published more than 32 research papers in national and international peer-reviewed Scopus journals. Under his supervision, 1 student awarded PhD and 3 students working for their PhD research. He has a teaching experience of 15 years in UG, PG level. Sir has been working on a major project of worth rupees 17.58 lakh by Science, Engineering and Research Board in 2019-20. He has completed 1 minor project also. He has delivered 16 invited talks at international, nationals and state levels, seminars, conference, workshops. He visited Atlanta, Georgia in USA in 2015. He has organized 3 conferences, workshops successively. He is a member of Board of Studies in 3 universities, institutes. He is a member of 5 different national, international academic bodies I express my sincere gratitude and gratefulness to you, sir, for having joined here to guide and enlighten us. Sir, your lecture will be very fruitful to us. Thank you. Over to Patel, madam.
Thank you, sir. Thank you.
Now I request Dr. Kishore Kuchi sir to enlighten us. Over to you, sir.
Thank you. Thank you. Thank you very much, ma'am. Thank you. I'm sharing my screen. Okay. Screen is visible to all of you. Please.
Yes, sir. Yes, sir.
Yes.
Okay. Thank you. Thank you very much. Good afternoon, one and all. I am very happy to deliver a talk in state level webinar on fundamentals of fractional calculus. Title of talk is Fundamental of Fractional Calculus. I know that there may be many participants which are doing research in fractional calculus, field of fractional calculus. But this talk I have prepared keeping in mind beginners working in the field of fractional calculus. Okay. I am not claiming for the material which I am presenting in this presentation. This material which I have taken, this material which I am presenting here is taken from the book, two books, one by Igor Podlumini and another is by Kai Dithel. Okay, that references I will show at the end of this presentation. Okay, so with this I will start. My outline of the talk will be like this. Firstly, we will discuss what is fractional calculus. Then we will discuss its history and development. Then we will discuss the properties of two most widely used definition of fractional derivatives. That is, one is Riemann-Levin fractional derivative and another is the Caputo fractional derivative. Then we will see the Laplace transform of these two derivatives and we will compare which derivative gives fruitful result to us. Then we will have a look on Mittag-Leffler function. Dear friend, we know the concept of first order derivative, second order derivative, nth order derivative and all. Similarly, we know the concept of first order integration, second order integration and n-fold integration. Now, what is the idea in the fractional calculus is to generalize the notation of differentiation and to generalize the notation of integration. We have to replace this natural order by any real order, or surprisingly, it may be your complex order. What is fractional calculus is actually, it deals with derivative and integral of any arbitrary order. It may be your real order or it may be your complex order. Okay, and it is called your fractional integral and fractional derivative. What is the aim actually in this field is that to generalize the notation of differentiation, integration, and to unify the notation of fractional derivative operators so that it gives derivative and integration simultaneously with a single symbol. Okay. Now, everyone knows that the conversation in the 17th century between Newton and Leibniz. And we know that Leibniz and Newton have developed a foundation of differential and integral calculus. And at that time, Leibniz introduced this symbol, nth order derivative of function f of t. And after invention of this, he reported this to mathematician L. Opita with n is natural number. And Leibniz asked, when Leibniz is given this information to L. Opita, at that time L. Opita replied him with the letter again, what will happen when n is equal to half, when we will put here in this symbol. At that time, Leibniz replied to him that it will lead a paradox from which one day useful consequences will be occur. And from last 3 decades, we can observe that there are a lot of application of fractional differential equation. Okay, and this letter by Leibniz was 30th September 1695. Therefore, 30th September we are considering as birthday of fractional calculus. Okay. Now we will see. We will have a look on development of fractional derivatives. So there are many definitions of fractional derivatives, and this definition generally does not coincide with each other. And possibly this is because of what every mathematician who is defining the fractional derivative operator, definition of fractional derivative, they would like to preserve the properties of classical derivatives. We know the concept of Riemann integration, basic concept. Okay. So after that, there are many concepts of integration. For example, take Lebesgue integration. So what we are checking in Lebesgue integration, whether all properties of Riemann integration is satisfied by that defined integral or not. Okay. So when we are generalizing any concept, whatever it may be, it must preserve the realistic property. Therefore, here also we are expecting, after defining the fractional order derivative, we are expecting that when we will replace the real order or say complex order by the natural number, okay, it must give your classical definition of derivative. There are different, more than, I will say more than 30 definitions are there for the fractional derivative because of this fact. Because unfortunately, what happened, whatever the definitions defined in the literature, they all are not satisfying the every property of the classical derivatives. But in another hand, many fractional derivatives in the modeling problem, they are giving nice result than your integer order differentiation. Okay, so I will listed here some classical fractional derivative. Most well-known definitions are Grunwald-Letnikov, Sono-Letnikov, Levy derivative, Riemann derivative, Caputo derivative, Hartmann, and these are the definition again. And these are some new fractional derivatives just in last decade have been introduced, which is first one is Machado derivative, Chern-Macedo derivative, Coimbra derivative, Cartan-Polar derivative, Caputo-Cartan-Polar derivative, Hilbert-Cartan-Polar derivative, and so on. And recently, in last 2 years, this definition has been introduced by Atangana and Balonu in the view of Caputo and Riemann-Levy, and this is Sahil for fractional derivative. On these two derivatives, I am working currently now. Okay, so whenever any mathematician would like to define definition of fractional derivative, they have to keep in mind that they must preserve whatever the fractional derivative is defined. That derivative must preserve this classical property. So any fractional derivative which is introduced, it must have the backward compatibility. Means what? When I am replacing, suppose I am denoting that fractional derivative by d raised to alpha, c capital D raised to alpha, and alpha is real number, say for example. And if I am replacing alpha by natural number, it must give a classical nth order derivative. That must be the first property preserved by your fractional derivative operator. Second property, if I am replacing that alpha by 0, it must give your function as it is, similar to your classical derivative. Means when we are define the symbol nth order derivative, when we are replacing n by your 0, it gives your function as it is. Okay. It must preserve this linearity property, which is preserved by the classical. These all property I have listed here for the classical nth order derivative. And what we are expecting, any fractional derivative must satisfy this property. But already I have explained that unfortunately none of the derivative till now, even though most widely used definitions are the Riemann-Levy derivative and Caputo derivative, these two derivatives are also not satisfying all the properties. The most properties are satisfied by Riemann-Levy derivative and Caputo derivative. So there must be the linearity for the fractional derivative property, commutation property must be there. Means if I am defining derivative, suppose alpha derivative and beta derivative are the two derivative with defined suppose derivative. So alpha derivative of beta derivative must be beta derivative of alpha derivative, that must be hold. Your semi-group property must be hold. If I am taking alpha derivative and beta derivative, the result generated must be same as when I am taking alpha plus beta order derivative. There must be the product rule for the fractional order derivative, and we must be able to define chain rule for that. Okay, so this property must be preserved by your classical derivative. Okay, so I will start the basic, start with basic. Suppose this integral, this Riemann integration, okay, if I am denoting it by operator IA from CAB to CAB, and if I am writing I of f of t is equal to this integration a to t f of s ds, okay, so Cauchy has proved that this n-time integration of this function can be written in the form of single integration. Okay, so we have the formula for n-time integration of the function f of t in the form of single integration. Okay, and we know it is very well known that any mathematicians are very interested in generalizing the concepts. They are believing in abstraction. Okay, so we know we have the generalization of this factorial notation in the form of gamma. Okay, so question surely rise that can we replace this n by real number, positive real number, and it works actually. because we have the generalization for the factorial notation gamma. Actually, this gamma function I have defined here for the real interval actually, but this gamma is defined for your complex number also, gamma of z. Same type of definition there, just x is replaced by your z. What is the required? Only real part of z is greater than 0, and we have to explain. We have to remove the poles. This gamma function has pole at negative integers including 0. Okay, so we have the generalization for this factorial notation. Means what we are expecting here, just after replacing factorial notation by the gamma function and n here by alpha, this integral must be exist, and it works actually. Therefore, we have the definition of Riemann-Leibel. What is there? Only this n alpha is replaced by factorial notation, and what happens if I am taking alpha greater than 0? This integral is exist, and this is the definition of Riemann-Leibel fractional derivative integral. Riemann-Leibel fractional integral of order alpha is greater than or equal to 0. When alpha is strictly greater than 0, at that time we are taking this definition of fractional integral. And when I am taking alpha is natural number, it gives your Cauchy results for the n time integration. And 0th order integration, we have to define f of t is equal to f of t. There is reason for defining this 0th order integration of f of t is equal to f of t, that we will see later in the next slide. Okay, so what is the requirement only for the existence of this integration is what? F must be the continuous. If f is continuous, this integration is exist alpha greater than, for any alpha greater than 0. Okay, so if integration is exist, there should be no hesitation for defining the fractional order integration, and Riemann-Leibel has defined in this sense. Okay, so if you are considering the two continuous function f and g, okay, so this fractional integral satisfies your linearity property, commutation law is hold for the integration, alpha order integration of beta order integration is same as beta order integration of alpha order integration, semi-group property is there, alpha plus beta order integration generate the same result when I am taking firstly beta order integration, then alpha order integration, and most importantly, if I am taking the limit of this integral, fractional integral as alpha tending to 0, this gives your result f of t. Okay, so this has this result has actually big proof which is provided in the book of Igor Podlomny, but just I have to give the flavor of this subject. That's why I am just recalling the results here which are important for your beginning of the study, and that's why because of this result, this is the reasonable to put 0th order integration of f of t is equal to f of t, which I have taken here. Okay, this is possible because of this result only. Now, when we consider the power function t minus a raised to mu, fractional integral of this is given in this format. Now, just look toward the definition of nth order integration of nth power of t minus a. And in classical integration, n time integration of this power function, we have seen this result, but using the definition of gamma function, we can write here this, okay, just extension, and we can compare that. See, both are resemble to each other. Moreover, if I am replacing here alpha in this definition by natural number and mu by a natural number m, I am getting this definition from your this Riemann-Leibel fractional integral of the power function. Moreover, what is the benefit here? Here integration I am not able to define for mu between -1 to 0, mu between -1 to 0. But here for the Riemann-Leibel fractional integral, I am getting the fractional integration of power function when the power function has power between -1 to 0. That is the benefit here for defining your fractional integration. Okay. Second, integration of constant is defined in this fashion: c upon gamma alpha plus 1 t minus a raised to alpha. And I have the formula for the integration. I can derive this formula, alpha order integration of exponential function, which is given in the form of beta-Gleiter function. This function I will define later. This is generalization of what your exponential function. Now, what we have considered here for the fractional integral is only power function, constant, and exponential function. Knowing the fractional integration of this function, I am able to define the fractional integral of other function, because you know that sine, cos, tan, cot, sine, sec, cosec, all trigonometric function I can express in the form of power function or in the form of exponential function, or even though logarithmic function has the power series expansion. So if I know the derivative or integration of power function and constant, I must be able to define the integration of what your trigonometric function, logarithmic function. Okay. So we have not considered the derivative of that functions here. Okay. Okay. Having the knowledge of fractional integral with us, I can define Riemann level fractional derivative. Okay. So if alpha is any real number which is positive real number, okay, for any real number, positive real number, I can find out two consecutive natural numbers, say n minus 1 and suppose I am taking real number 1.2. What is the number sandwiching? What is the n for that is 2, because I can sandwich 1.2 in what 1 and 2. Okay. So for any alpha greater than 0, the two consecutive number that sandwich alpha is n minus 1 and n. With knowing this n, I can define your Riemann level derivative, alpha order derivative in the form of this classical nth order derivative of n minus alpha order integration. Okay. Now, if you observe the definition of fractional derivative, if you observe the definition of this Riemann level fractional derivative, see, this is your classical nth order derivative of n minus alpha order integration. If I am writing this alpha order n minus alpha order integration in the form of inverse of derivative, sometimes we are creating integration as inverse of derivative. So if I am writing derivative of minus order n minus alpha, and if I am taking the using the indices law, you will see that n and plus of minus n minus alpha is generated your L alpha. So this may be the reason behind defining the alpha order Riemann level derivative in this form. So just what I have to do here, I have to find out the natural number n satisfying this condition. Okay, and after knowing this n, alpha order derivative is defined in this sense. Nth order derivative, this is classical derivative of fractional integration n minus alpha. The elaborated form of this is this. So this Riemann level fractional integral I have elaborated here in this format. When I am taking alpha is between n minus 1 and n, when alpha is not equal to n. But when alpha is equal to n, see here, put alpha is equal to n here, n minus n is 0. And already I have shown that zeroth order integration of function f of t is f of t. So I am getting this format. So what is the benefit of this Riemann level derivative is that if I am taking alpha by natural number, I am getting your classical definition of derivative. Okay. So second thing is that if alpha is between n minus 1 to n, and if I am taking limit of this Riemann level derivative as alpha tending to n, I am getting again your classical derivative. When I am taking alpha tending to n minus 1, I am getting your n minus 1 classical derivative. So what happened that this Riemann level derivative act as a bridge between two classical derivative. That is what nth order derivative and n minus 1th order derivative. Because in classical derivative, we know the derivative of nth order, we know the derivative of n minus 1th order. And before defining the definition of fractional derivative, we are unable to calculate the derivative of real order. Okay, so now after defining Riemann level derivative, we know the derivative of nth order, we know the derivative of n minus 1th order, and we can fill gap between n and n minus 1th order, n minus 1 and n. So I can now I am able to find out the derivative of order alpha between n minus 1 to n. So I can say that this derivative act as a bridge between these two classical derivatives. Again, one thing is that I can put here zeroth order derivative of f of t, zeroth order Riemann level derivative of f of t is equal to f of t. See here, if I am taking alpha, n is equal to 1, take here n is equal to 1. So 0 less than alpha less than 1, and take alpha tending to 0 here. See, alpha tending to 0, zeroth order derivative of f of t. So I am getting f of t is here. Okay. Now, just we have defined this definition of Riemann level derivative. Nth order derivative, Leibniz formula is here. Okay. Now, to define the nth order derivative at t, everyone knows that the classical derivative has definition in the form of limit, and to define the limit as x tending to t, t must be the limit point of the domain. And you know that definition of limit is in the form of neighborhood. Every neighborhood of t must contain the points of domain of f, so that I must able to say that x is tending to t. Okay. So to define this classical derivative, any type, any order n, I must know the function in some arbitrary neighborhood of t. Okay, that's why we are saying that this classical derivative is your local derivative operator. But to define this Riemann level derivative, I must have the information of the function f from a to t. Otherwise, I can't define this. If I do not know the function f between the interval a to t. Okay, that's why we are calling this Riemann-Leibniz derivative as a non-local operator. I can explain this non-locality after deriving its equivalent integral equation, but just for the sake of understanding here, I have explained here what is the locality of this classical derivative and non-locality of this fractional derivative. Okay, again, we have the derivative formula for the power function in this format, and if alpha is between n minus 1 to n, t minus a raised to alpha minus m, its alpha order derivative has 0. And see, this is your classical formula, classical derivative formula. Nth order derivative of t minus a raised to m gives in this format, m greater than or equal to n, and if m is less than n, nth order derivative of power function is 0. Okay, now if I am replacing here n alpha by n, mu by m, okay, I am getting the similar type of formula, same formula here as produced in classical case from this. Okay, and what is the again more benefit? I can't calculate here derivative of order t minus a raised to something, say minus half, because I am getting singularity here. But what is the benefit here? This formula is available for mu greater than minus 1, means I can define the Riemann-Leibniz derivative of the power function when mu is between minus 1 to 0. Okay, I have the formula for the constant here in this format. But friends, we know that classical derivative of constant is 0 here in classical case, and this is the drawback of Riemann-Leibniz. The first drawback which we came across is that Riemann-Leibniz derivative of constant is equal to G, not equal to 0. Okay, I have the formula for exponential function in the form of Mittag-Leffler function. Okay, and knowing the derivative of constant, exponential function, and power function, I am able to define the derivative of other trigonometric function and what we call your other logarithmic function and exponential function. Okay, so these are the properties of Riemann-Leibniz derivative. So I explain the first property. Suppose alpha and beta are the two real number which are positive. Okay, and if I am going for the calculator, these are the actually theorems. This is first theorem, second theorem, third theorem, like that. But I have collected in the single formula. So alpha order derivative of beta order integration of f of t generate in this format. Alpha minus beta order derivative in the sense of Riemann when alpha is positive. If alpha is equal to beta, I am getting alpha order integration of alpha order derivative of alpha order integration is equal to f of t. Similar as in the case of what is that your classical case. If I am taking integration of n order and if I am operating the nth order derivative on that, I am getting the function as it is. Okay. So same type of result is generated here for the classical case also. Riemann-Leibniz case also. Okay. Now this is the generalized formula, integration of derivative. But I have taken here the different powers. Beta is real number and positive real number. Alpha is positive real number here. And if I am considering alpha is between n minus 1 to n, this is the formula for integration of derivative in this formula. But if I am taking alpha is equal to beta, I am getting this result. Now, we know this. This is your classical case. Nth order derivative of f t. If I am operating n time integration on it, I am getting this result. F of t minus. This summation is nothing but what your n plus 1 terms in the Taylor expansion of f of t. Okay. Now similar type of result is generated here. But what is the drawback again? This is second drawback which I am which came across here. Okay, I am getting here initial conditions in the form of fractional derivative, but in classical case I am getting the initial conditions. Suppose some differential equation is given. You have seen PG students. I am particularly speaking to the PG student. You have studied your E. Coddington book. Okay, now to study the nonlinear differential equation, what we are doing, we are forming the equivalent integral equation for that. Okay. But when we are forming the equivalent integral, at that time, after integration, the initial conditions are generated in the form of unknown function at initial point and its derivative at the initial point. Okay, so this is because of this formula. Okay, function and its derivative are known in the classical sense, but this is not case here. That's why when we are going for the modeling of any problem in the form of fractional derivative in the sense of Riemann-Leibniz derivative, this trouble, This make trouble because we have no geometrical meaning as well as physical meaning for the fractional order derivative. Okay. Now, as in the classical case, see here your classical nth order derivative in nth order integration, it generates your identity. Means if I am taking some function here, it function is generated as it is, but integration of derivative is not your function. It comes with some additional term. See here, that is the term here. And same cases happen here in the case of fractional derivative also. Okay. Now we will see the composition, how the composition rules work for your Riemann-Leibniz derivative. Suppose this is your classical derivative, because already I explained that if I am taking alpha, some natural number, it reduces to your classical derivative. So you can take this is your Riemann-Leibniz derivatives also. Okay. So Riemann-Leibniz derivative of integer order of Riemann-Leibniz derivative of real order generate this result. I am getting m plus alpha order Riemann-Leibniz derivative. But this is not the case. I am not getting the same result when I am taking firstly real order derivative and then mth order derivative. This come with some additional quantity. So semi-group property fails here. But I have the commutation property fails here. I am getting this property, but I am not getting these two quantities same with because this additionally come here. Okay. So in generally, your Riemann-Leibniz derivative operator does not commit. It commits with certain assumption on the function. To vanish this term, this power function is not vanished for all t. This gamma function is constant. So what must be 0 here to get these two quantity equal? This kth order derivative of f at a must be 0 when k equal to 0 to m minus 1. Okay. So commutation law for Riemann-Leibniz derivative with integer order holds only if your function must able to satisfy this condition. Then I can expect. Okay. Now, second thing is that with this property, firstly taking mth order derivative, then alpha order derivative, this generate this result. With using this property, I can write alpha order derivative in this format when alpha is between n minus 1 to n. Now see here, when alpha is between n minus 1 to n, this power, if I am denoting it by beta, that will be surely in your 0 to 1, between 0 to 1. Okay. So any order, real order, positive real order derivative in the sense of Riemann-Leibniz, I can write in this format. This classical n minus 1th order derivative of beta order derivative. But beta is between what your 0 to 1. Okay. And I know the property of classical derivatives. Therefore, to study the behavior of Riemann-Leibniz derivative, it is not necessary to go for any real order. It is sufficient only for beta between 0 to 1. Okay. Therefore, when we see the literature of fractional differential equations or fractional calculus, maximum properties or maximum theory for the fractional differential equations has been developed with power between 0 to 1 because of this result. I can express alpha order derivative in the form of this result because I know the property of classical derivative. See, now we will see the composition of Riemann-Leibniz derivative, one Riemann derivative with respect to another derivative. So suppose I am taking two derivative, alpha and beta. Alpha is between n minus 1 to n say, and beta is between m minus 1 to m say. Okay, so alpha order derivative of beta order derivative is in this format. After changing the role of alpha and beta, I am getting this result. Again, you can say that these two are not same. Alpha order derivative of beta order derivative is not same as alpha plus beta order derivative. It comes with some additional quantity. So this quantity must be 0. Okay. So again, to hold commutativity law and semi-group property for Riemann-Leibniz fractional derivative, your function must be able to satisfy this condition. Kth order derivative of f at initial point must be equal to 0 when k equal to 0, 1, 2 up to r minus 1, where r is maximum of m and n, this m and n. Okay. Now Leibniz formula is there. As in the case of your classical derivative, what is the change? Only here I am getting n minus kth order classical derivative in the place of this fractional order derivative, and this k equal to 0 to infinity runs up to n only if I am replacing alpha is equal to n. But in the case of Riemann-Leibniz, this series go up to infinity because this combination alpha choose k, this combination alpha choose k does not vanish for all the k. That's why the Leibniz rule has this infinite series. Okay, this result you can see in the book of Igor Podlomny. Okay, now we will go for the Laplace transform. This is your Riemann-Leibniz derivative. Laplace transform generate this formula. But if you see the classical derivative, its Laplace transform, it has in this format. Now, you can observe that Laplace transform of nth order derivative is generated in the form of kth order derivative. This is classical case. Classical case. Okay. So initial value for any differential equation, when I am taking the Laplace transform, your initial conditions are generated in the form of zeroth order derivative, first order derivative, second order derivative, to which I can give the meaning. Suppose if I am supposing x of t, x is displacement at time t. Suppose I am speaking t equal to 0, what you will say that displacement at point 0, that is your initial condition. If I am taking its derivative, x dash at t, velocity at t. So if I am taking t equal to 0, what you call velocity at time t equal to 0. Similarly, x double dash has acceleration. But as we know, fractional derivative has no geometrical meaning. It is the drawback actually here. And this is another drawback. When I am applying Laplace transform to Riemann derivative, it does not generate your initial condition in the form of classical case. Okay. So surely there is need for the another derivative to in the view of applied problem. Okay, so that we'll see later. So these are the limitations which I have listed here for the Riemann derivative. Okay, Riemann derivative of constant is not equal to 0. Okay, that I have mentioned here, and this might be issue when using RL derivative for writing the differential equation. When I am taking limit of this derivative as t tending to it gives infinity. This might be issue when applying to the boundary condition, and the Laplace transform of RL fractional derivative depends on the fractional derivative at 0. Okay, and this might be an issue when solving initial value problem, because while we are considering any physical phenomena, if you are considering any physical phenomena and we are modeling in the form of differential equation, we have to take into account the initial conditions at initial point, which has the geometrical meaning and which is not appear here in the case of Riemann level. Okay, that's why we need another derivative. So keeping in the mind practical applicability, the Italian mathematician M. Caputo has defined this definition, that is called Caputo derivative of the function f of t. Again, on the similar line, we have to find out the natural number n minus 1 n consecutive to natural number with sandwich alpha. Okay, so Caputo derivative of f of t is defined in this sense. N minus alpha, this is fractional integral in the sense of Riemann level, and this is your classical nth order derivative. And this is the elaborated form of it. Take alpha is equal to n, so n minus n is 0. Zeroth order integration of function is as it is, so I am getting nth order derivative here. Okay, and when alpha is not equal to n, means alpha is strictly between n minus 1 to n, at that time this is your definition of Caputo. So from this definition you can see that when I am replacing alpha by natural number, I am getting your classical definition of derivative. That is the beneficial for us. Now second thing, when taking alpha tending to limit n, suppose I have defined alpha order derivative and I am taking limit alpha tending to n and alpha tending to n minus 1, I am getting upper consistency. Okay, but I am not getting the lower consistency. Here I am, this is an additional term coming here, which is not the case in your Riemann level. Okay, now this is fractional integral of Riemann level, fractional integral of Caputo derivative. This is the formula we'll get after applying fractional integral of alpha order on Caputo derivative. Okay. And observe, this is our classical case, which we are studying from right from 12th standard, nth order derivative, nth order integration of nth order derivative. I am getting in this format. Now compare this. Integration of derivative in the sense of Caputo generates your initial condition in the form of classical derivative, kth order derivative, as in the case of your classical case, as in the case of your usual classical case. Okay, that's why when we are considering the differential equation in the sense of Caputo, my initial conditions are generated in the form of first order derivative, second order derivative, and so on. Okay, and that is beneficial for us because we are able to give the geometrical meaning to it. Again, some derivatives I will list here. Most important thing is that Caputo derivative gives zero derivative for the constant, which is not in the case of Riemann level. I have the power, I have the derivative for the power function, which again resembles with our classical case. I have the exponential derivative of exponential function in the form of Mittag-Leffler, so that I can have the derivative of other functions in the form of constant and power function and exponential function. Okay. As in the case of Riemann-Liouville, Caputo also not satisfies your commutativity property as well as what is that, your semi-group property in general. I am speaking. It satisfies under certain condition. Your kth order derivative of function must be 0 when k is equal to n plus 1 up to m, where m is equal to 0, 1, 2, 3, and so on. Okay. For any integer m, and from where this n came? N came from this inequality. I have to find out the natural number n and n minus 1 to which alpha is sandwiched. In between that, alpha is sandwiched. Okay. Again, using this property, see, alpha order derivative of mth order classical derivative is your alpha plus mth order Caputo derivative. Using this property, I can write any order alpha order derivative in this format. Okay. So again, if I am denoting this quantity alpha minus of n minus 1 by beta, then that beta is between what is 0 to 1 again. Okay. So what is that? This is fractional derivative of classical derivative n minus 1. And we know the property of classical derivative. Therefore, again, to study the Caputo properties of Caputo derivative or behavior of the Caputo derivative or fractional differential equation with Caputo derivative, it is not necessary to consider any real order. Just if you are studying between 0 to 1 order, it is sufficient for real order, because any real order can be converted in this format. Because I know the property of classical derivative. Just I have to concentrate on beta between 0 to 1. Okay. Now, this is your definition of Riemann-Liouville derivative when alpha is between n minus 1 to n, and this is your definition of Caputo derivative. But we know that derivative of integration is not equal to integration of derivative. This is in the fractional case. Similar is hold for your classical case also. Classical in Leibniz calculus, same thing is hold. Okay, so we can't expect that these two derivatives are same. Though these two derivatives are not same, but it has relation between these two. Suppose we are assuming Riemann-Liouville derivatives exist and Caputo derivatives exist for f of t. Caputo derivative can be expressed in the form of Riemann-Liouville. Okay, and these two derivatives are same only in the particular case that your function kth order derivative must be 0 for k equal to 0 to n minus 1. In that case only, and it does not happen for all the functions. Okay, Leibniz formula is there, which we can extract from your Riemann-Liouville derivative formula for Leibniz. Okay, because there is a relation between Riemann-Liouville derivative and Caputo derivative. This is the important thing again. If I am applying Laplace transform to Caputo derivative, this result is generated. And if I am replacing alpha by a natural number, I am getting this formula, same formula, similar type of formula as in the classical case. See, observe, just replace alpha by n here. So I am getting your classical case. Okay, so Laplace transform formula for the Caputo derivative coincides, resembles with your Laplace transform of classical nth order derivative. Okay, and most important thing is that Laplace transform of Caputo derivative has functions and its derivative at the initial terminal in the classical sense. It will be beneficial when we are solving the initial value problems. So these are the important aspects of the Caputo derivative. It gives constant derivative equal to 0. When t tending to a, it gives derivative 0. This is suitable for applying to boundary value problem. Okay, and Laplace transform of Caputo fractional derivative is the generalization of Laplace transform of integer order derivative. And the same thing is not hold for the Riemann-Liouville derivative that already I explained. Okay, so when we will consider Riemann-Liouville and Caputo, so we can think that which derivative is most important, but we can't say that Riemann-Liouville is very better than Caputo or Caputo is more better than Riemann-Liouville. They have their own values at their own places, because that thing I will explain later. Just I will compare this. Laplace transform of Riemann-Liouville derivative involve initial value of the fractional derivative, but Laplace transform of Caputo derivative involves your initial functions. Laplace transform of Caputo is actually generalization of what your Laplace transform classical case. Okay, and a definite. But what is the definition? For the defining Caputo derivative of any function, I require the integrability of Fn. Okay, so for Riemann-Liouville case, in the Riemann-Liouville case, I can define the Riemann-Liouville derivative of the function which has the integrability only. Okay, continuity is sufficient for defining Riemann-Liouville derivative, but for defining Caputo derivative, F must have satisfied this property. I need the nth order derivative must be exist and its integrability is required. So that is that restrict the class of class for which Caputo derivatives exist. Okay. So we surely think that which derivative is better. So already I have explained that Riemann-Liouville derivative has its own value, Caputo derivative has its own value. Okay, I can say that Riemann-Liouville derivative is more superior than your Caputo derivative, and Caputo derivative is more superior than your Riemann-Liouville derivative. Okay, because Riemann-Liouville derivative plays important role mainly in development of theory of fractional derivative and development of your pure mathematics. But Caputo fractional derivative has importance in applied problem, where it requires a proper definition of fractional derivative for the applications. Okay, therefore Caputo fractional derivative more suitable for the applied problem. Okay, now if I am considering your nonlinear differential equation, so just I am considering your simple differential equation which we have came across at PG classes also. In E. Coddington book, say, or whatever the book you are using, y dash is equal to ft yt. So I am y dash I am replacing by your Caputo derivative here, and it gives this existence result, first existence result I will call. So if this alpha is between your 0 to 1, okay, and k is greater than 0, and if I am considering a rectangle, this is your rectangle, say, and if I am assuming f is continuous on this rectangle, then if I am defining this quantity t is equal to b if m is equal to 0 and t is equal to minimum of b and this quantity, otherwise if m is not equal to 0, m is equal to 0 is possible only when f is equal to 0 sometimes. Okay, so if f is continuous on this rectangle and it is bounded by m, then this initial value problem has solution in the space of continuous function from 0 to t. So this is your existence result. Okay, and this problem can be converted in the form of this equivalent integral equation. Okay, now if I am considering alpha is equal to 1 here, it gives to 0, and I am getting the same type of equivalent integral which appeared in the classical case. Okay, now from this result one can think that if f is continuous, we know that Riemann integration of continuous function is again continuous. So if y is continuous, if f is continuous, okay, I am getting this total function is continuous and y naught is constant, it is continuous. So for the Caputo fractional differential equation, continuity of this function f, implies the continuity of solution. So when your function f is continuous, I am expecting the solution is also continuous. See here, just I have explained here. See, this is your classical case. It has the formula in this equivalent integral equation in the form of equation 4. Same can be generated from here if I am taking alpha is equal to 1, because for alpha is equal to 1, this Caputo derivative reduces to what your classical derivative, y dash. Okay, so same type of result is generated here. Now, I can explain non-locality in different sense. So, if I am considering this integration and take any two values, t1 and t2 between 0 to b, and calculate, suppose t2 is greater than t1, and calculate your yt2 minus yt1 from this expression 2. Okay, so I am getting this yt2 this value and yt1 is this value, and after rewriting this I can get here. Okay. Now if I am considering alpha is equal to 1 classical case, what will happen that your alpha equal to 1, this term gets 0 and I am left with this. Okay, so in that case your yt2 minus yt1 is generated in this format, and suppose I know the value of yt2, yt1, y at t1, and I have to calculate the value in future time, say t2. Okay, to calculate that I must be rely only on yt1. I must rely on yt1 only, value of y at t1 only, and the function f alone. Okay, in this classical sense. And to calculate the value of y at t2, I do not know. It is not necessary to know y at t between 0 to t1. So this y must be known only between t1 to t2 to calculate the value of any point t2 in the interval suppose if I know the value of y at some point t1. But when I am considering the fractional case, okay, this is never vanishing for any value alpha between 0 to 1. Okay. Therefore, if I know the value of the state, I will call y is state, suppose, of your physical system. And if I know the value of y at t1, and to calculate the value in future, say at t2, I must be able to know y at 0 to t1 also and t1 to t2 also. Okay. So, to calculate the value, I must be able to know the value of the function y from 0 to t2 to calculate the value t2, which is not the case in your real. Okay. Therefore, this is another view of your non-locality, explaining the non-locality. So therefore, I have written here observation. The first integral on the right-hand side of C does not vanish in general. Hence, whenever we want to compute the solution y22 at some point t2, it is necessary to take into account the entire history of y from 0 to t2, which is our vintage state value. So this reflects the non-locality of Caputo fractional derivative. So that already I have explained in the previous slide also. Now this is your Mittag-Leffler function. We know that exponential function, which we have studied, e raised to z is equal to summation z raised to n upon n factorial, that plays very important role while dealing with linear ordinary differential equation, because we know that linear differential equation with constant coefficient generates the solution in the form of exponential function. Now, to deal with fractional derivative, linear fractional derivative with constant coefficient, we require a function like exponential function, and that is done by this. In classical case, we are expecting the solution in the form of exponential function. Similarly, in fractional case, we are expecting the solution in the form of Mittag-Leffler function. This is two-parameter Mittag-Leffler function, which is generalization of this. Okay, when I am taking beta is equal to 1, I am getting one parameter Mittag-Leffler function. When I am taking alpha is equal to 1, it generates your exponential function. When I am taking alpha is equal to beta is equal to 1, I am getting exponential function here. So that we have mentioned here. Okay, so already I have explained Mittag-Leffler function is generalization of exponential function. The exponential function plays important role in the theory of linear integer ordinary differential equation, but Mittag-Leffler function plays a role in the study of linear fractional ordinary differential equation. These are some functions which we have calculated. E raised to z in the form of one parameter Mittag-Leffler function. Cos hyperbolic function I can generate from a two parameter Mittag-Leffler function. If I am taking alpha is equal to 2, beta is equal to 1, and in the place of z, if I am taking z square, cos hyperbolic is generated. Similarly, I can calculate sin hyperbolic, cos, sin, cos. And if I know e raised to z, sin, cos, sin hyperbolic, cos hyperbolic in the form of Mittag-Leffler function, I can generate other function, because sin, cos, tan, cos, sec, cosec can be expressed in the form of trigonometric function sin and cos, or in the form of exponential function. Okay, so this is the result which is important. Already I have explained. I can calculate if I am taking here y dash in the place of Caputo derivative, this constant of variation parameter formula I am expecting in the form of exponential function. But when I am considering this case, Caputo case, derivative case, okay, the solution for this 7 problem is in this format. If I am taking alpha is between 0 to 1, this is the case. And already I explained, if I am taking alpha tending to 1, this is converted to your classical case, and exponential function is converted to your exponential function. So see, 9 and 10 is converted in this format, and which you have studied at graduate level and postgraduate level. Okay, so when I am considering your differential equation, integer order differential equation, this is your constant of variation parameter formula for the solution in the form of exponential terms. Similar type of formula I am expecting here. A similar type of formula we have generated here for the Caputo fractional differential equation, linear Caputo fractional derivative with constant coefficient in the Mittag-Leffler sense. Okay, so I think it is sufficient. So I have revised all the basic related to your Riemann-Leibniz derivative and Caputo derivative, and explain the importance of your Riemann-Leibniz derivative and Caputo derivative. So these are the references which I have referred for preparation of these slides. Main references for me are this book by Igor Podlomny, this one, Kilbas and Srivastava, and this book I did him. Okay, other are also very important book. If you are interested for further study, you can refer this for your fundamental study, basic study. Okay, with this, thank you. If you have any question, I will be happy to give the answer of that. Thank you. Yes, madam, please. Khare sir.
Thank you very much, sir, for such a wonderful lecture. Now participants
Thank you, madam.
Participants can turn on their mics if they have any questions. Is there any question?
So complete 1 hour sharp. We have started at 12 o'clock and it is completed at 1 o'clock.
Yes, sir. Is there anyone?
Anybody, if you have any query, otherwise we'll stop.
If you have any question, then just put it in the chat box. Okay. Now. I feel extremely happy and honored to invite Honorable Dr. P.S. Yankar ma'am for presidential speech.
असं सध्या 2 मिनिटं थांबा ना, म्हणजे तुम्हाला बोलायचं असेल तर. ओके सर, थँक्यू सो मच. हॅलो.
Yes.
Hello, Kishore sir.
Yes, please, sir, please.
Hello, yeah, a very good afternoon to all of you.
Good afternoon.
At the outset, principal of Vidya Bharati Mahavidyalaya, I welcome today's speaker, Dr. Kuchi, for having accepted our invitation and sparing time and enlightening all the participants. I'm sorry I could not join you people today, though I am a person of literature, but it is always my attempt to listen to such wonderful talk so that my knowledge is also a little bit enlightened because of that. But somehow I could not do so. I came to know that the lecture was very interesting. Just now, Khadija reported it to me. Welcome you, sir, for joining us. I also welcome all the participants. Just now I was informed that there are participants from various parts of India, IIT, Hyderabad, IIT Vellore, UP and Tamil Nadu. Of course, I congratulate Dr. Khalid for taking special efforts and making this webinar so wonderful and so successful. I also congratulate Patil Madam for helping him out and organizing this webinar. Well, we all can see that even though it's a pandemic period and we are not able to meet physically, we are not able to conduct seminars and workshops and conferences, but see, we should always be optimistic. There is always a way out. It is said in English that if you think of good, so something good comes out. Where there is a will, there is always a way. So because of this digital platform, we all are connected. So let us thank the modern technology for it. And I'm sure today's webinar will be of great help for all participants. I once again thank you, sir. Thank you, Kuchi sir, for being with us. Thank you, all the participants who are connected to us. And yes, we as Vidya Bharati, we have always been trying to go ahead with all the latest and modern technologies, and we try to provide such kind of atmosphere, a very healthy research culture on our campus. And I expect the same kind of a cooperation from you people even in future. Thank you so much.
Thank you.
Thank you, sir.
Thank you very much. Thank you very much, ma'am, for your warm address. Now it is my privilege and pleasant task to propose a vote of thanks for this webinar. I express my hearty sincere thanks to Honorable Shri Rao Sahib Shekhawat Sir, Honorable Mrs. Manjari Shekhawat Ma'am, Honorable Secretary Dr. A.D. Chauhan Sir, Honorable Principal Dr. P.S. Yankar Ma'am, Honorable Dr. R.M. Patil, sir. I would also like to thank the eminent speaker, Dr. Kishore Kuchi, sir, to enlighten us by delivering such a wonderful lecture. Thank you very much, sir. I
Thank
would
you, ma'am.
also like to thank Dr. P.P. Khade, sir, for the success of this webinar. I would also like to thank Dr. Katore, sir, Dr. Kandalkar, sir, Dr. Pawar, sir, Dr. Mete, sir, Dr. Bondar, sir, Dr. Bayaskar, sir, and Dr. Nimkar, sir, for their remarkable presence. I would also like to thank all the participants for sparing your valuable time for this webinar. I'm also thankful to all teaching and non-teaching staff for their valuable support. And with the permission of Chair, this webinar is over. Thank you.
Thank you. Thank you, ma'am. Thank you. Thank you very much.
Thank you, Kuchi sir. करून दे.
थँक्यू सर.